I'm a scientist myself. I started out as a string theorist in the same class as Robert Dijkgraaf and Erik van Lindenburg, and I was destined to be staying in science if it were not for something in my personal life that I decided to go back to the Netherlands. So I worked for Shell already now for 30 years. I didn't sever the ties with university. I have a relation or an appointment at MIT. And I'm still deeply fascinated by energy as I was back then. You can see my own telescope. I'm both interested in how nature chooses to use energy, I will come to that in a minute, but also what the dominant energy source is in the universe, which is fusion, of which I also think there is a bright future for us. It's very clear, also in Shell, I can assure you that we want to have more of these. There is no debate that we really need to scale up renewables beyond a scale that is presumably even unbelievable to many. What, however, is an issue is that when you start to get out of your lab into the real world and think about scale, then there are three things that you need to worry about. Not in order of importance, all of them are important, but let's say start at the top. The economics have to work at scale. Of course, it needs to be at scale also because fighting climate or global warming is a systemic problem, a global problem that cannot be solved just by local initiatives and then forget about how they link to others. And as we've sadly seen also now in Europe, for I think the second time since 1974, security of access of energy is very vitally important. These things are integrating into a policy perhaps at the end of the day, and where the trade-offs are made is a debate that we should have in the country, in the parliament, but also amongst ourselves. Focusing on one or the other is not helping us really, because it will lead to delay. The economics is relevant to actually get you to scale. If it comes to scale with solar and wind, then one of the things that you're hit by is that they take a lot of space. And that is because the so-called power density of wind and solar is demonstrably lower, in fact very much lower, than, let's say, of hydrocarbons, whether they're fossil or something else, it doesn't matter, or nuclear. As you can see here, what happens if you replace oil that can be replaced by hydrogen, for example, and you insist that the hydrogen is made by green electrons, you need a lot of wind farm area, or for that matter, solar farm. You can calculate this, and if you see this little dot somewhere with an arrow, that's the footprint that a nuclear reactor would have, producing the same amount of hydrogen. There's nothing fundamentally against this. It will just take time to convince everyone to build this. And because that it will take a lot of time, and probably also quite a lot of investments, you should worry, are these really the best places to build solar and wind? It's probably clear that in the North Sea a lot of wind is relevant, certainly in the northern North Sea, maybe even north of Scotland. But whether solar farms are that good of an idea in Europe, given the fact that we are faced with some of the weather most of the time, as we see here, is perhaps another question. And intuitively, it's very clear where you would like to build solar farms, in the deserts. In the desert, the solar radiation is fantastic, and there is a lot of space. Empty space. And it's also true, as some people might have done the thermodynamics of that you don't need a lot of solar panels to power the entire energy system. The energy system on Earth is actually not that large compared to the amount of energy that the sun dumps on us every day. In fact, you need 500,000 solar panels in square kilometers, 500,000 square kilometers. Easily, I would say. What is not so clear is that they are far from where we live. And one of the problems with electricity is that it doesn't transport beyond 1,000 or 1,500 kilometers as cheaply as it does below. And it is also, and that's related to that same question, not easily storable. Again, those technologies will advance, for sure, but the cost will increase. The cost of hydrogen, for example, can become unaffordable. So we're faced with a transport problem if we really want to scale up a lot of renewables, as well as a storage problem. And that storage is presumably most hitting us for heavy industries where that storage needs to be done on an annual or seasonal base. And there are solutions to that. In fact, nature shows you what a solution is. Namely fatty acids, if you wish, or maybe for the chemists among us, hydrocarbons. A godwit, I'm a keen birder, as you might have known, still seen now, has an ability to fly non-stop 11,000 kilometers. It does so with an absolutely phenomenal efficiency, and also it does something that few planes are able to do, namely to take their weight in fuel more than 50% at takeoff. It therefore has an enormous amount of energy density stored into this to make this journey. It can make this journey very flexibly. You don't know what the weather will be and what routes to take. Recently we were able to prove by putting sensors on these things that they also fly straight over the Himalayas, actually climbing to altitudes of around 7,000 meters. That's not a mean feat for such a small bird. It's only the Dreamliner that comes close to a similar energy density and efficiency. Not quite yet, but it is coming close. And why is that? Well, nature has actually showed us that linear hydrocarbon chains, or for that matter, these three structures that you see here on the left in fatty acids, are actually a phenomenal good way to store energy. And the fact that you can store energy at arbitrary timescales means that you can probably also transport it very quickly. Shell in the past has actually developed this higher olefin process that actually builds on the same theme. This is used as a base in kerosene. What I'm actually getting at, that rather than perhaps focusing entirely on direct electrification, chemical energy carriers, not for making products, but chemical energy carriers to transport and store energy, so that the most advantaged places to resource production, like deserts for solar or windy areas, far away from where we live possibly, can transport it to any customer in the world at the lowest possible cost. That's where the economy comes in. If you can't do that, scale will be limited. So hence, if you are able to build solar farms or wind farms close to where you live, for sure you would do this. But that will not be enough for the large industries that each of these three populating areas I just showed you, eastern US, northwestern Europe, northeastern China, the Ganges Delta, or the Ganges valleys in India, are far away from deserts and are also not particularly well known for their windy days. And hence this transport problem starts to hit you, as well as the storage problem. By focusing on chemical energy carriers, in addition, not replacing it, but in addition, that are made clean in an energy resource and carbon resource system that doesn't show any fossil hydrocarbons, we have the ability to power people's lives or users according to their power densities in much more versatile ways, in a way that actually drives down cost. And that will get us to scale. Why do I insist on that? Well, that's what the oil industry has done over the last 60 years. Most people, of course, identify the fossil hydrocarbon industry with the fact that it deals with fossil resources. But what makes the oil industry big is the fact that it scales because of the transportability and the storability. That allowed us, after the Second World War, to get oil and gas from anywhere at the lowest possible cost. It therefore favored those areas where the resource production can be done most optimally, either because of its availability or because of the fact that not many people living there, or there is simply a cost attractiveness to do it there. Super basins, they're called. And indeed, 90% of all oil today comes out of less than 40 super basins. These are these red blobs here. Incidentally, some of them are also very good to actually build wind farms in, or solar farms. So those energy basins are essentially perhaps a good starting point to create, also because there is a lot of chemical factories around there or nearby, already. And hence it might lead you to the production of these energy-dense carriers, chemical carriers, for transport and storability, either at the site where you produce them, or say at the site where you actually will deliver that, if you can, say, given that by direct electrification. So I'm actually very positive that we can scale up, that this dynamic, this ability to really develop a large-scale system that allows you to combine economy with access and security of access, as well as being able to do this cleanly, is something that an oil and gas industry knows how to do. In contrary to what most people believe, the fact that we produce hydrocarbons is only part of the business. The growth in this business, after say the 1940s, is really due to the transport and the storability of the stuff that we sold. And that can be done again. And if you now look forward, in 2050, we need to scale up a net zero emission system. A system, for example, that looks at this, that does contain nuclear. I do think nuclear makes imminent sense, in particular advanced nuclear at small sites, at chemical sites, say, to balance, say, the rough edges of renewables that might not be as available or would drive up the cost, might actually lead to an acceleration. That systems integration at a very large scale, far away from the lab, if you wish, but built on solutions in chemistry, in physics and engineering from the lab, is what companies like Shell have done for 60 years. What you're looking at, this system today, is actually a product of that. And hence, I cannot predict the future, but what I can predict is that we will see a flurry of activities of how to produce these chemical energy carriers. For example, by offshore platforms. Our offshore engineering industries are very good at that. Where you moor, say, an ammonia factory in a wind farm, or produce hydrogen. I have 20 seconds left. And this is in fact my last slide. Those things are known. You can use existing infrastructure, modify it, so you don't have to start from scratch. Thank you very much.